Hey everybody, this is Mr. Trenitsky, and this is AP Stats 3.4 to 3.7 quiz. Okay, in question number 1, we have a plot of some data points for a population increase in the bald eagle, and we've done a regression on that and gotten a least squared regression line, which has a pretty strong correlation coefficient of 0.989. That's really good. But we're wondering, is the linear regression actually the best one? That's actually the best fit for our data. The correlation coefficient seems to tell us it fits really well, but if we look at the residual plot, we can see there's this clear curved pattern going on here. So it is not going to be the best fit. Something else like a exponential or power is going to fit better in our data. Okay. So A is incorrect, B is incorrect, C is incorrect, D is incorrect. Okay, the linear model is not, linear model is not appropriate. So it's either D or E, and the reason that it's not appropriate is the clear pattern in our residual plot. So the correct answer is E. Question number 2. It's speculated that hitters in baseball with more home runs also have more strikeouts. A random sample of 13 players was selected. For each player, the number of home runs they hit for the season X compared to the number of strikeouts in the Y. And we have a linear regression line, and we have our scatter plot here. So the question is, we have a point down here at circled that's considered an influential point. So it's influential for a couple reasons, mainly because it's very far on the x-axis away from our center point of our least squared regression line. It's also pretty far away vertically too, so it's going to have a lot of influence on our line. And the question is, if we were to remove this point, how would our line change? Okay, so right now this point is pulling on that line down, so you can think of it as a string, and if we removed it, it's like snapping that string. Our regression line is going to come back and fit better into the rest of these points. So our slope is going to increase, okay, and our y-intercept is going to decrease. Those two things are going to happen if we took out that outlier, which is answer C. Question 3. Residual plots from 5 different least squared regression analyses are shown below. Assuming a strong correlation between the variables, which residual plots provide the strongest evidence that a linear model is appropriate? So when we're looking at residual plots, the biggest thing we want to see is no pattern. Total randomness. Points above, points below, points above, points below. No curves or Christmas trees or fire hoses or anything like that. So that eliminates A, because it has that kind of Christmas tree pattern here. C, because we have that clear curved pattern. And D, also because we kind of that, again, reverse Christmas tree pattern going on here. So the correct answer is going to be B. Oh, and E also has a curved pattern. So that one is no good either. So B is the correct answer. Okay. It is often helpful to estimate the weight of fish based on its length. Length and weight measurements were taken on 42 pike, and 2 different regression models were created, where X is the length of the fish in inches and Y is the weight of the fish in pounds. The first two regressions. So regression A yielded y hat equals negative 34.07 plus 1.2834x. So that's the equation for regression A. And then regression B yielded log y equals log x. And we plotted the residual plots from both of those. So regression A is showing a clear curved pattern on our residuals. So that one is not any good, okay? Whereas regression B has plenty of scattered randomness in its residuals. So this one is going to be the better residual plot, okay? So, which means there is a non-linear, because A was the linear, and B was the non-linear. We used the log y and log x. So there's a non-linear relationship, and the better regression is going to be B. Okay. The relationship between the price of a rectangular rug y in dollars and its area x in square inches is modeled by the equation y squared hat equals negative 64.853.01 plus 21.40.39 x. Use a model to predict the price of a rug that has 74 square inches. So to do this one, we're going to simply plug in our x value of 74 square inches. So we'll plug in 74 there. Go to our calculator. Punch that in. So negative 7, 4, oops, clear. Negative 6, 4, 853.01 plus 2140.39 times 74, and we get 93,535. And we might be tempted to circle letter D, but for one issue is that is not our y value, that is our y squared value. So what we need to do in order to solve this is we need to take the square root of both of those. So take the square root of our previous answer, and we get 305.83. .836 or really 84, which is answer A. Okay. Question number 6. Researchers are examining the amount of disruption to the forests around the world due to human activity. Two characteristics being examined are the basal area of the dominant tree species, so the area, basically the area of forest, and the number of tree species that are in the forest. So basically the more comparing the amount of area you have of forest compared to the number of species that you have. Different species. Okay, and we have a least squared regression line. Our data from that is there, okay? And they plotted the residual. So looking at the residual, is the least squared regression line an appropriate model for the data? And it's not terrible, but I'd still see a curved pattern. Okay, it's pretty clear curved pattern. We're starting above, going below, and then coming back above our zero line here in our residuals. Okay, so no for A. The residual plot shows a curved pattern. Use the least squared regression line to predict the number of tree species in the forest where the dominant tree species has a basal area of 7.4. So our equation would look like this. Our y value is tree species. Tree species hat equals, so our constant, or y-intercept, is right here. So 148.132 plus the slope right underneath it. So that's our basal area slope. So actually, let's put a minus 12.36 times the basal area. So there's our equation. All we're going to do is we're going to plug in 7.4 into that equation. So plug in 7.4 for our basal area. Go to our calculator to do that. So 148.132 minus 12.36 times 7.4, and we get 56.668. Tree species. Always make sure to use your units. All right, based on the residual plot, is this prediction calculated in part B an underestimate or an overestimate of the actual number of tree species? So looking at our plot here at 7.4, that is this point right here, and we can see that is under our prediction line. So the prediction line is an overestimate of our actual value. So it's an overestimate. We can see on the residual plot 7.4 is a negative residual. Okay. The forest where dominant trees species has a basal area of 7.4 has 37 different tree values in the forest. So basically, this is telling us this actual value here, right there, that is actually 7.4 comma 37. So we're trying to figure out what is that residual. Okay. So you take your actual, that 37, minus our predicted 56.668 minus 56.668, and we get negative 19.668. as our residual. Meaning that our plot over predicts by almost 20 tree species.
Attention CCEA membership. Thank you so much